This lecture is the first of our vector differentiation. Differentiation in multiple dimensions. And the first one is quite simple. It's a vector path. So the kind of stuff we're going to cover are different kind of vectors. So the first one is the path. That means given some time point, where is a particle in space? That means the position, the x and y, is just a function of time. Yeah, that's all it is. So where you are as you walk through the world can be described as a continuous function, and the only thing that changes is time, and that tells you your new position. So that means it maps one dimension, time, into 3 dimensions. That's what this lecture is going to be about. The other kind is you have 3 dimensions and you map it to 1. So for example, you know a location and the function describes the height. So you have x, y, and z, or the azimuth and the elevation of position, the longitude and latitude, and you know the height. So you have a function that maps this into 1 number. And lastly, our vector field f. A vector field can take any dimensional variable and map it to any dimension possible. So in this simple example, it maps a 3-dimensional variable to 3-dimensional. Okay, and there are the 3 kind of basic functions we're going to look at. So first, our vector path. So a simple vector path here is you have an x component and a y component. Yeah. And so in this simple example, we just have starting at 0, 0 or -5, it goes up, 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 dot, 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 dot. And that's your vector path. Yeah. The next one, TT, just means they go on a diagonal line. Think about it. When time is 0, it's at 0. When time is 1, it's 1, 1. Time 2, it's over. Up, 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 up. Yeah. And then you can get more complicated looking functions. And this is how you can get loop-de-loops. So x is t and y is t squared. And we get our parabolic looking shape. Yeah. It goes down and then back up. Yeah. And then you have more interesting shapes where you have squared. Yeah. Where you can have a shape like this. And you can move in different ways. Yeah. One of the most common ones is the circle. A unit circle. So when t is equal to 0, the cos of 0 is 1, sine of 0 is 0. So we start here and it just goes round and round. As t changes, the angle changes. And that's what we have here, something that goes round and round and round. That is our path. So for every single time point, we're at a different position. Now we could be at the same position at different time points, but every time point has a position. And then it can get more complicated. You can have a nice spiral. And the reason why you get the spiral is you have that t times cos t and t times sine t. As time gets bigger and bigger, the circle gets larger and larger and spirals out. So you can make very complicated patterns very quickly from just simple functions. And now we move to 3 dimensions. X, Y, and Z. That's not a great X, Y, Z. X, Y, and Z. Yeah. So in my example here, this is very straightforward. Z is 2, it always stays the same. So it just moves around and around the same height. Here, the next one, Z changes a function of time. So what happens is as time gets longer, it goes higher and higher, but it's always spiraling. So top down, it just looked like a circle. And our last example, t cos t, as time gets larger, it expands out and spiral. But it's a function of t, so it goes up as well. So you spiral out. Yeah. So you have a function like that. So we've done the recap of differentiation. We know that the derivative of a line is the slope. Derivative of a function is the rate of change. So what does it mean for one variable to another? What does it mean in our scenario here? We have our rules, which we've gone through. So in a path situation, so this is a general form. Any function in any dimension described by time. So generally you keep it to 3 dimensions. But if you're in quantum physics, you go to 11 or 13. Yeah. What you have to do then is differentiate each of these with respect to time. So this is just like a single variable differentiation, but you do it for each function. So if you have a function ft is 1t, what's the derivative of it? Derivative of 1 is 0, derivative of t is 1. And so that gets you the rate of change in the x direction, xy direction is not 1. But what do we have here? That graph, if we remember, was just the dots going pop, 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 pop. Yeah? So why is 0 in the x direction? Because x doesn't change, doesn't move left or right. And y is just constantly increasing. Yeah? So that's what it's saying. So what you now have is, at this point here, you move up. You're at the next point, you move up. That's what the derivative is saying. It's saying, if you're at a certain point, where do I go? That's what it's telling the direction you should move. So now if we have the t, remember the graph was dot, dot, dot in a diagonal line. So derivative of t with respect to t is 1. Derivative of t with respect to t is 1. So we get the vector 1, 1. What is a vector 1, 1? It's a diagonal vector. And that's saying that if I'm at a point, I go diagonally away, diagonally away, diagonally away. Makes sense. And now we get to our more interesting examples, our t and t squared. We have our graph here. So we differentiate this. It's always the same in the x direction. It's always 1, 1, 1. Yeah. But in the y direction, the derivative of t squared is 2t. So when t is negative, when time is negative here, it's 1 put in minus 4 minus 8 goes down. Yeah. And it goes down as it goes negative. And then we get to here and it's 0, 0. So actually we're at a minimum. But as soon as we come out of that, you go up. And what happens as t gets larger, the steps get bigger. So for a t of 100, you go 1 step in the x direction and 200 in the y direction. That's what we have representation here. Yeah. Similarly for t squared and t cubed. Derivative of t squared is 2t. Derivative of t cubed is 3t squared. And so you have this lovely graph. Let's start with a negative t. You start here and you work your way up. And that's what the arrow is. Each of these, at each time point is telling you the direction it will go next. Yeah? That's what we have with a path. You know the direction it's going to head. And lastly, and this one takes us a couple of seconds to think through. Sine, cos is the x direction. Sine is the y direction. Yeah? So, as t changes, what happens? Well, as I say, you start here and you go round and 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 round. Yeah? The derivative of that, derivative of cos t is minus sine t. Derivative of sine t is cos t. So what happens is, at this point here, the derivative is saying it's going up. You are going up. That's straight up. But then as soon as you move in there, it starts saying that way, and it moves you around. Yeah? So when you're here, it says you're moving down. You are moving down, but then you come in. Yeah? So that's what we get when we have a path. Any movement, doesn't matter how many dimensions, I've done 2 here. We'll do higher dimensions in the tutorial. You can find out where it is and what direction it's going. Yeah? And that's what we have with a path. And that's also the beginning of a vector field. If you understand that at any point, you know from its derivative direction it's going, then you know what a vector field is. You understand that actually. So that's one particle flowing through water. How do you describe all particles flowing through the water? And that's what we're going to come to over the next while. So that's our first introduction into vector differentiation. It's a path, so it's very straightforward. It's just for one variable. But from this point on, we're going to look at multiple variables.